Is celestial mechanics deterministic? Victor Szebehely. Abstract. It is shown that conditions for deterministic systems are neither satisfied by those dynamical systems which are encountered by actual physical situation, nor by problems of interest in celestial mechanics. Introduction. Our undergraduate dynamics textbooks offer examples which, almost without exceptions, are solvable explicitly. In other words, these mostly artificial problems are not only integrable, but even more elementary than the problem of two bodies, the solution of which, as it is well known, cannot be expressed by simple explicit functions of the time. One of the purposes of this paper is to correct the erroneous impression created by our elementary dynamics textbooks, and to correct and clarify the misleading teaching of many naive teachers. Deterministic versus non-deterministic dynamical systems. Dynamical systems existing in real life usually have the following properties. The systems are not integrable. i.e., the number of globally valid integrals is smaller than necessary to reduce the system to an integrable form. In some very special cases, when the system is integrable, such as the problem of two bodies, the solution of the reduced differential equation is not solvable with known or elementary functions of the time without infinite series. The dynamical system may be represented analytically either by a system of differential equations or by its Hamiltonian or Lagrangian functions. All of these representations are approximate since the actual real physical systems usually contain either unknown influences or effects which are excluded from the analytical description because of their complexity. In short, our analytical representation is approximate, and the effects of neglected terms are unknown, especially for long times. The initial conditions, which in principle determine the solution of the system, satisfying, say, the Lipschitz condition, are known usually only approximately. An excellent example of this is the behavior of a mass-length particle in the restricted problem of three bodies that is placed, initially with zero velocity, at any of the equilibrium points. In general, the initial conditions in the configuration space are not rational numbers. The ordinates of the triangular points contain square root of 3, while the abscisse of the collinear points are solutions of fifth-order algebraic equations. Numerical integration of the motion of particles placed at the triangular libration points do not start exactly with the proper initial conditions, and even in the case of critical stability, the integrated orbits are not the expected fixed points, but move away from the equilibrium positions. At this point, it seems to be proper to define problems which belong to deterministic dynamics as those which do not encounter any of the above listed four difficulties. This leaves us with an empty set of real-world problems, since deterministic dynamics exists only in our childhood dreams, or in Laplace's fantasy, according to Poincaré. It should be added that one of the serious consequences of the non-deterministic nature of problems in celestial mechanics is that meaningful long-term predictions, especially as t approaches infinity, are difficult or impossible to obtain. Examples in celestial mechanics. Concerning the previously mentioned restricted problem of three bodies, the effect of irrational numbers as initial conditions at the equilibrium points easily qualify this problem as one of the simplest examples for non-deterministic dynamics. In addition, the model of the restricted problem is an approximation to all physical problems for a number of reasons. The third particle of infinitesimal mass always has finite mass. The primaries seldom move on circles as required by the model. The problem is non-integrable as shown by Poincaré in 1896. And finally, regions of the phase space show great sensitivity to initial conditions. To emphasize this last point, we attempted to establish regions of the configuration space, Szebehely and McKinsey, 1978, for libration motion and for chaotic, irregular behavior in the vicinity of the triangular libration points. In these numerical experiments, no sharp and clear separation could be established between these two regions because of the high sensitivity to initial condition of the qualitative behavior of the system. Instead of listing the many other existing examples concerning the restricted problem, a few other systems, popular in celestial mechanics are listed shortly. The problem of determining the high-order gravitational components of the Earth via satellite observations belongs to non-deterministic dynamics. As it is well known, satellites launched in different orbits will give different values of the J, Ij gravitational coefficients of the Earth. The inverse problem of the above, i.e. the long-time determination of satellite orbits, belongs also to non-deterministic dynamics, partially because of our ignorance concerning the model used, especially when drag effects are of importance. The construction of planetary ephemerides encounters all the above-mentioned problems. The initial conditions have been accurately observed for a very short time compared to the life of the system. The gravitational many-body problem is non-integrable. Therefore, either generally divergent series solutions or numerical integrations must furnish the results. Both approaches lead to undeterministic dynamics, especially for long-time predictions. Predictions concerning the behavior of stellar systems or galaxies also serve as excellent examples for undeterministic dynamics because of the non-integrability, the weakness of the physical model, and of the unknown three-dimensional initial conditions. It seems to be clear that if the dynamics of the artificial Earth satellite is undeterministic, then our ability to offer long-time deterministic predictions for the motion of galaxies is non-existent. The same applies to planetary systems. Conclusions and future expectations. The seriousness that celestial mechanics belongs to the group of problems known as non-deterministic dynamics is not unexpected, and it is neither to be underestimated nor to be considered hopeless. Just to mention two examples where significant progresses have been made, attention is directed to the method of regularization used in modern celestial mechanics and to the introduction of surfaces of section mapping techniques to help our understanding of the behavior of the system. The non-deterministic nature of celestial mechanics is to be considered a challenge rather than a criticism. Criticism must be applied, on the other hand, to those who use self-deception or by misleading statements attempt to justify its deterministic nature. Unquestionably, artificial and non-natural problems may be invented in celestial mechanics, just as in elementary dynamics, which may be solved deterministically. These problems and their solutions may result in regression rather than progress in celestial mechanics. Progress should be expected from the acceptance of the non-deterministic nature and from the developments of new topological statistical techniques to deal with the presently unsolved problems. Acknowledgement. The author gratefully acknowledges the support received in the preparation and presentation of this paper by the NATO Scientific Affairs Division, by the Johnson Space Center of NASA, and by the University of Texas. Discussions with Professor Ilya Prigozhin influenced essentially the ideas expressed in this paper.